So this question is about the optical properties about polymers, and you might need to ask Dr. Harding specifically what he meant in some of these, because I actually am not sure myself. And it's asking in part A that if we look above 400 nanometers, we can ignore the absorption index. So above 400 nanometers, up through 800 nanometers, which is roughly the visible range, the index, it tells us the index of refraction is 1.58, and it wants us to estimate the fraction of light that is reflected off the polycarbonate sample surface. So this is a bit of a funny question in my mind. If you can imagine a polycarbonate material in cross-section, and this particular material is exposed to some sort of incident light, and that there are several things that happen to that incident light as it moves through the polycarbonate material, and you have an exiting light. Now what we know is that the light has to do one of three things. It either has to be transmitted, it has to be absorbed, or reflected as it enters the surface. So we know that in the end, one of these three phenomena will account for the initial fraction of light that was incident on this polycarbonate sample. In the question, it says that there is no absorption. So whatever is not transmitted is reflected, and in this data set, it shows that the transmittance is approximately, for polycarbonate, 98%. No, that's 88%. So therefore, what is reflected is approximately 12%. So I'm going to skip this part B because both Dr. Harding and I can't exactly figure out if maybe there's a typo in the question or something. I'm not really sure about this part B. So part C asks why these polymers form amorphous structures based on their mirror structure. So of course you have to kind of look at these structures and know that the formation of crystalline polymers, or crystallinity in polymer structure, really relies on the polymers being able to rotate within the chains, the bonds, and fold back along itself. So anything in the MER structure that is going to complicate or resist that rotation is going to make it less likely to be crystalline. And there are a few things that would inhibit the crystallinity. One of them is if you had extensive branching along the polymer chain, so that you would simply have, sort of steric hindrance for that folding structure. Another thing that could hinder the folding along itself is having covalent molecules that will not rotate. And another thing that could hinder the structure is having polar regions on the polymer itself, and polar regions that would have a tendency to be attracted to other polar regions in a separate molecule. So that would just provide the molecule with greater stiffness, such as you see in PVC. So these polar regions right here in the oxygen areas are likely to hinder the crystalline structure. So the reason these have sort of a polarity is that carbon and oxygen don't have an equal pull on the electrons. So the oxygen has a stronger pull, stronger electronegativity, so the oxygen is likely to be, presented as a negative region inside this molecule. So this last question is about whether we expect polycarbonate to have a higher or lower glass transition temperature than polymethyl methacrylate. And in answering this question, it's helpful to remember that the glass transition temperature indicates the temperature below which you don't have enough energy, thermal energy, to to rotate the atoms in the chain. So what this says is, you know, the lower the glass transition temperature is, it indicates that, you know, you can continue to rotate that molecule along the chain, you know, the covalent bonds of the chain, down to lower and lower temperatures. So it actually doesn't require very much thermal investment in order to do that. So the higher the glass transition temperature, by contrast, indicates that you have to invest a lot more thermal energy in order to activate that degree of freedom to rotate those bonds. So what I would guess is that as you look at these two molecules, is that you see that along the backbone of the PMMA, you have just carbon-carbon bonds. And then along the backbone of the polycarbonate, you have an array of different bonds. You have carbon-oxygen bonds, you have bonds to carbon, and then double bonds within this hexagon here, and then different types of bonds along the chain. So it would be my guess that polymethyl methacrylate, having these similar, just simple carbon-carbon bonds, would actually have a lower glass transition temperature than the polycarbonate.